These industrial chemical plant towers represent the massive scale of modern manufacturing. This entire infrastructure relies on elimination reactions, the primary process used to create energy-rich carbon-carbon double bonds. To understand these reactions, we start with the simplest single-step pathway, the bimolecular elimination, or E2 mechanism. For a molecule to forge that new double bond, it must lose two specific groups, a leaving group and a proton from the adjacent beta carbon. In this 3D model of 2-bromobutane, notice the timing. As the blue base abstracts the green beta proton, the red leaving group departs at the exact same moment. Bond breaking and bond making happen simultaneously. This concerted timing defines the E2 pathway. If the sequence shifts, if the leaving group departs early or the proton is removed first, the reaction branches into entirely different mechanistic territory. This frozen E2 transition state shows the spatial requirement for the reaction. For the evolving p orbitals to overlap and form a stable pi bond, the reacting bonds must be coplanar. This forces the proton and leaving group into an anti-periplanar alignment, 180 degrees apart. A syn-periplanar alignment also satisfies coplanarity, but rotating into this position forces the electron-rich base into direct proximity with the anionic leaving group, creating massive electrostatic repulsion. When there are multiple beta protons to choose from, a small base like ethoxide targets the internal position. This follows Zaitsev's rule, forming the most highly substituted and stable alkene. Contrast that with the right side. A bulky base like tert butoxide encounters internal steric resistance. It is forced to abstract a peripheral terminal proton instead, yielding the less substituted Hofmann product. The final product is the result of a constant tug-of-war between thermodynamic stability and kinetic accessibility. Unlike the synchronized E2 pathway, the E1 mechanism is stepwise. It begins with the slow, rate-determining departure of the leaving group to form a planar carbocation intermediate. Because this carbocation is a discrete intermediate, the molecule can undergo structural rearrangements, like a 1,2 hydride shift, moving the positive charge to a stable tertiary carbon. The E1CB mechanism inverts the sequence. A base removes an acidic proton first, forming a stabilized carbanion, which then expels the leaving group. Apply these rules to rigid rings. Look at the chair conformations of neomethyl and methyl chloride. Pay close attention to the axial and equatorial positions. Neomethyl chloride reacts quickly because its chlorine is already axial, aligned for elimination, but methyl chloride must undergo a high-energy ring flip to force its chlorine axial. This creates an enormous activation barrier, slowing the reaction by a factor of 200. The spatial requirement for orbital overlap takes precedence. The molecule yields a less stable alkene if it's the only pathway allowed by its three-dimensional geometry. In practice, elimination pathways are always competing against nucleophilic substitution within the same reaction flask. The outcome depends on the target. The reagent can act as a base by attacking a peripheral proton, or it can act as a nucleophile by attacking the electrophilic carbon. Applying heat shifts the distribution toward elimination. In this Gibbs free energy visualization, notice elimination splits one reactant into 3 distinct products. This entropy increase means as temperature rises, the T delta S term becomes larger, lowering the free energy of elimination more than substitution. Biological systems use this same logic. During glycolysis, the enzyme enolase coordinates an E1CB dehydration to forge the enol phosphate bond that powers cellular metabolism. To keep these straight for your exams, use this matrix. E1 and E1CB involve carbocation or carbanion intermediates, while E2 is concerted. Each pathway reacts differently based on sterics and regioselectivity. Substrate sterics set the mechanism, the strength of the base directs the thermodynamic route, and three-dimensional geometry determines the final chemical product.